Welcome to Module 2 of Digital Signal Processing. In this module, we are going to see the basics of digital signal processing, and we will start by considering discrete time signals and operators on discrete time signals in Module 2.1. In Module 2.2, we are going to consider complex exponentials. These are the most elementary and fundamental discrete time signals. Finally, in Module 2.3, we're going to take building blocks, elementary ones from signal processing, to see some elementary operations on signals like moving averages and recursive filters, and finally build a simple synthesizer. Let's now get started and see what discrete time signals really are. Module 2.1, Discrete time signals. The overview is the following. We will define discrete time signals to know what we are talking about here as a main component in the class. We are going to look at different types of signals, give examples, and then go on to operators, which are elementary blocks, building blocks for more complex systems that will be used in discrete time signal processing. And finally finish with two concepts which will come also over and over in the class, which is the energy of a signal and the power of a signal. What is the earliest discrete time signals we can think of? Well, probably the earliest ones that has been recorded are the floods of the Nile. So the Nile, of course, is extremely important in the agriculture of Egypt, and so from very early on, people recorded how high the Nile would come in any given year. And this representation has been caught here on this beautiful historical record that is about 4,500 years old, and is a representation of the flood data. Unfortunately, we don't have a digital version of this data, so we can't really do signal processing on this. Maybe somebody wants to pick up a research project and actually do this transformation. In the meantime, we have access to more recent data. So this is an example of the flood in the Nile in cubic meters per second, yearly measurements over the last 100 years or so. You can see the representation is these lollipop diagrams. So the lollipop is at any given year, we represent one data point. So we have here almost a bit more than 100. It's a very busy signal, but overall, even if you just look at it approximatively, you can sort of see there is a trend, okay? And the trend is not a good one. It means there is less and less water in the Nile. The second example of a signal is daily temperature. It's probably your first scientific experiment. Every day at 8 a.m. you look at the temperature outside. You do this every day for a year, for a couple of years, and so on. And you record something that could also be a lollipop diagram like in the previous slide, except there are so many points here that we decided to actually join them, so it looks almost as a continuous time function, even though it's one measurement every day over a few thousand days. Now, when you look at this, you of course immediately see that there are seasons happening. So the temperature here in centigrades, goes up and down with a yearly variation. And this we can actually show. We can fit the sinusoid, here the blue curve that has been added, and this is simply the trend that is due to the seasonal change in daily temperature. Now, this blue sinusoid is actually one of the things we are going to do here in the class. We're going to take a data set, like the original data set, and we're going to fit the sinusoid, and there are algorithmic methods to actually do this. The next signal is so-called solar activity. So as you probably know, the sun has different intensity due to solar spots, and this has been measured over several hundred years now. And we again see this curve here, which has a lot of variation. It's not seasonal variation. It's a different variation, and we shall also analyze this variation later on in the class. Now, all the signals so far had to do with physics. Now we can see a man-made signal, that's a world population, from the beginning of current times, until now, and you see that it's a slowly evolving curve up to the Industrial Revolution here. This is the Industrial Revolution. And then for various reasons, which are not the topic of this class, there was a population explosion. By now we are close to 8 billion, and it's not completely clear what's going to happen next. Another man-made signal is the value of the stock market. Here it's a Dow Jones, and again it's something that looks a little bit like the world population in the beginning, so very small. Then there is an exponential increase. Then there is the internet bubble and the financial crisis, etc. Okay, so there is a good question mark. What is going to happen next? We could claim that thanks to signal processing we can predict the future of the stock market, but I'll be honest, this is a very hard problem. If we knew how to do this, we probably wouldn't be teaching a free online course. We would be doing something else for a living. But anyway, it's a typical discrete time signal. You can measure the Dow Jones every day and record this as we did here. Again, it would be a lollipop a stick diagram, but here we have joined the points because there are so many points over this period of time. So let's be a little bit more formal. We saw several examples. All of these examples were a number per day, a number per second, a number per year. In the general case, this number can be a complex number. So for us, a discrete time signal is a sequence of complex numbers. We will look at mostly one-dimensional signals, and the dimension typically is time. The notation that's very important to note is that x is the name of the signal, then we have a square bracket, and finally we have the index n, which is an integer. We typically have two-sided sequences, so they start from minus infinity to, let's say, x minus 1, x at 0, x at 1, etc., and goes off to plus infinity. And the index is dimensionless, so it could be seconds, years, microseconds, or whatever, but we just index it as a dimensionless integer index. The analysis of a signal means we take periodic measurements. This is a topic that we will study in detail under the name of sampling. So for example, in the case of the Nile, we took a sample every year. In the case of the stock market, every day. And synthesis is when we generate a sequence of samples. We will see this when we talk about the Karplus-Strong algorithm later in this module, where we indeed generate a musical signal by generating discrete time samples. So among the formal signals or elementary signals we will be used in this class, we have, for example, the delta signal. The delta signal, denoted by delta of n here, is very simple. It's the simplest possible signal. It's 0 everywhere except at the origin where it's equal to 1. Okay? Now, do such signals exist in reality, or is it a pure mathematical abstraction? It is an abstraction. Most signals will not be that simple, but let me show you one signal which comes close to that. Let us look at an actual device called a clapper that is used in Hollywood studios to synchronize audio and video. Why do they need this? Well, sometimes the audio is recorded on one machine, the video on another machine, and later you have to splice them together. And so the way it is done is that you use this clapper, you write on what scene is shot by what director in what movie. And what you do is that you have the clapper that is open, you put it in front of the camera, then you close it, and that gives a click sound. And we see the click sound here at the bottom, and it's not exactly a Dirac, it's more complicated, but it is really an impulse, an impulsive sound. When you listen to it, it sounds like a Dirac. When you look at it in detail, it has oscillations because it's a piece of wood that is going to vibrate. But to a first approximation, this is as close as it gets to a Dirac. The next simple signal is a so-called unit step. It is a sequence that is 0 from minus infinity till the origin. At the origin, it flips to 1 and is 1 everywhere after that. Okay? Does such a signal exist in reality? A physical implementation would be a switch, like this blade switch that we see here. We call this a Frankenstein switch. If you have seen the movie, Dr. Frankenstein at some point gives life to the monster, so he flips a switch, a blade switch, and then some current flows into the monster that comes alive. So that's a beautiful picture of one of these blade switches. The third signal that is very typical is a so-called exponential decay sequence. So it's a combination of two things. Okay, it has a unit step, so the signal is 0 before the origin, and then it is positive. And at that point, we apply an exponential here with a root a that is smaller than 1, taken to the nth power, and so it nicely comes down as an exponential. Okay. If we did not apply the unit step, then of course the exponential would grow up here exponentially, and it would be unbounded. So that would be not a signal you would encounter in practice. So we see here a signal that has been specifically engineered that it looks actually like a signal that you would encounter in real life. And real life is coffee. So the way coffee will lose its temperature is governed by partial differential equation that we see here. It goes actually back to Newton, one of the greatest scientists of all time. So the law of cooling says that the rate of cooling is proportional to the difference of temperature between the cup of coffee and the environment. Okay, and there is a constant c here that says how fast actually the temperature will decay. The negative sign means the temperature will go down when the coffee is warm and the environment is cold. And the solution of the differential equation is given here, and it has indeed an exponential term. There are some practical issues. You have only convection at work, and there has to be sufficient conductivity. And then you will see a decay that looks a little bit like this. Okay, and here, let's say the ambient temperature is 0. We start with the coffee at 100 degrees, boiling water, and it will start to decay like this, and the speed of decay will depend how much convection there is, how much conductivity. Okay, so this was all to show you a little bit a sense of you have physics at work and you see signals in real life. A discrete time version of these signals will be typically sequences we'll be interested in this class. The next character in the play is the sinusoid. So here is the sinusoid indicated as sine of frequency omega naught times n, the index, plus a phase theta. Okay. In the drawing, we see theta is equal to 0. Actually, it's not equal to 0, I'm sorry. Theta is equal to pi over 2. So at the origin, it's maximum, and then we have the sinusoidal variation. Now, sinusoidal signals are everywhere. The heartbeat is an example. The whistle on the whistle used on a train that we'll also analyze later has sinusoidal components. Waves that are showing up on the shore are another example of sinusoidal component, and of course musical instruments really live off strings that have sinusoidal modes, something we'll also study in detail. There are really 4 classes of signals, and each one of them is a natural example of a signal and is used in different cases. The first one, the simplest one, is the finite length signal, then the infinite length sequence, periodic signals, and finite support sequences. Let's look at each of them in a little bit more detail. So a finite length signal can be either written in the sequence notation, so the sequence notation we have seen before, x of square bracket n, but n is only going from 0 to n minus 1, so it's a length capital N signal. The vector notation puts this into a vector, and in this class vectors are column vectors, so we have the entries of the vectors x0, x1 up to xn minus 1 and a transpose to get a column vector. Finite length signals or vectors are very useful, for example, in numerical packages like MATLAB and so on. Infinite length signals. We again have the sequence notations that we had seen before, and the index n now is from the integer set, meaning from -infinity to +infinity. This is very good for abstraction, for theorems, for analysis, using Fourier analysis, for example, Z transforms that we'll see later. But of course, in real life, unfortunately, nothing lives from -infinity to +infinity. That depends a little bit on your beliefs, but if you believe in Big Bangs, then it started at some point, and if you're not certain about reincarnation, it will stop at some point. So the sequence notation is really a mathematical abstraction. Periodic signals. We talked earlier about sinusoids, so periodic sequences do exist also in real life. They are denoted by x tilde. Okay, so the notation here, tilde, means there is a periodicity, and it means that xn is equal to xn plus k times the period. So capital N is the period, k is an integer, it means how many periods we shift, and n is the usual index for time. So one of these periods of length n has all the information needed. The rest is just a repetition. Okay? And very often periodic signals are a bridge between finite and infinite length signals, because you start with a finite length signal and maybe you let the period go to infinity, or you take a periodic signal and you let the n, the length of the period, go to infinity. A finite support sequence is defined by x over bar, given here, and it's a sequence xn that is only different from 0 for n between 0 and n minus 1. It is 0 otherwise, and it has the same information as a finite length signal of length n, and it is another possible bridge between finite and infinite length signals. Now that we have seen elementary signals, let's talk a little bit about operators. So if we have a sequence, we can scale the sequence by multiplying it with scalar alpha. Okay, so the natural thing is you have a sequence like this, you multiply it by 2, it's going to look the same, it's simply going to have amplitudes twice as large. The sum of two signals is obvious, you take two sequences and the result will be the sum of the two. The product of two sequences, same story, you take two elementary sequences xn, zn, you multiply them term by term, and last but not least, very important, the shift by k, or the delay by k. So k is a positive integer, so when we write yn is equal to yn minus k, then yn is a delayed version here of the sequence x, namely by k terms. We're going to look at this in detail. It's sometimes a little bit confusing, but if you want to think about it very quickly, is that y of 0, so the output sequence at 0, is equal to x of 0 minus k, so x of minus k. This is in the past, so it is the signal x from index minus k. Let's look specifically these shifts on the various types of sequences we have seen. So the shift of a finite length sequence, well, we have on the left side the original sequence, which is this decaying set here of samples, and we are going to shift it by extending this sequence with zeros left and right. Okay, so that's the only thing we did, is that we added zeros before the 8 samples and after the 8 samples. And if we shift it, well, we delayed by 1, so it is shifted right. And what has happened is that a 0 showed up here and the x7 fell off on the right side. We see this here at the bottom, that we can follow what happens as we shift further and further. Okay, shift by 2, again it is delayed by 2, so we have 2 zeros at the beginning, 2 samples that fall off, and we see the result at the bottom right side. And shift by 3, shift by 4, and you see the idea. We can also have a model of the world where the signal is periodically extended, and then the shift operator will have another effect. Let's look at this. So we start with the sequence, 8 samples from x0 to x7. We extend it periodically. Okay, so here we have a second period, here we have the previous period. And now, when we shift, what will happen is that we have a shift to the right, okay, x tilde n minus 1. So x7 enters on the left side, and x7 leaves at the right side. Okay, so the new signal, given here at the bottom right, has x7 entering here and having left on the other side. Now this, of course, is the same as doing a circular shift. Okay, let's do a few more. So x tilde n minus 2, we have now 2 new samples entering and 2 that fell off there, and at the bottom right we see the picture again. X tilde n minus 3, same story, x tilde n minus 4, one more step, and you start to see what is happening here. We have now seen the shift operator, which is one of the most fundamental ones we are going to use over and over again and study in great detail. Let's talk about 2 conceptual characteristics of signals. The first one is something we call the energy. The energy is the sum of squares of the samples. Okay, it is given in the formula here. So you take a sequence, you take the absolute value of the samples, you square it, and you sum from minus infinity to plus infinity. This may or may not be finite. If you take a sinusoid, it's a signal that starts at minus infinity, goes to plus infinity, has amplitudes that vary, let's say, between minus 1 and 1. And of course, if you square it and you sum from minus infinity to plus infinity, it will blow up. Okay? So a notion that can still be defined even for such signals that might have infinite energy is a notion of power. The notion of power is that you look at the energy over a window. The window is of size 2n plus 1, right? Because we sum from minus n here to plus n, the sum of squares. But we normalize this by the length of the window. So we put a 1 over 2n plus 1, and this is the power, because it's like the instantaneous energy for this sequence. So for periodic signals, as I have already alluded to, the energy will be infinite, and the power is simply the energy of one period divided by the length of the period. So this is given down here. So this part is the energy, 1 over gives the power, and this typically will be actually finite even when this guy is infinite. End of module 2.1.